But anyway, guys, cool. So I'm super happy to be presenting here, and just wanted to go over some basics about Solana. So this is going to be a really good presentation for anybody who's maybe like never built on Solana before, or maybe doesn't know much about blockchain, things like that. So this is going to be the presentation for you if that's kind of the category you fall into. So we'll cover all the basics about like how Solana kind of works, how you build on it, how you deploy to it, and things like that. So without further ado, I'm going to start sharing and we're going to just get right into it. And by the way, there will be space for Q&A, so you guys can totally ask questions. I believe the crew is bringing around some mics and stuff, so if you have questions as we're going, feel free to do so. You guys can pretty much just interrupt me, and I'm happy to answer those questions. So as you can see, here's the things we're going to cover, right? So we're going to cover why Solana, some core concepts, and the programming model, and some stuff about transactions, right? So it's going to be very like technical focused. But first of all, before it does get technically focused, we're going to take a look at why Solana is hot, right? So if those of you guys who don't know, or maybe you haven't heard, we are introducing a new RPC client, a new validator client, actually, the Fire Dancer. And this is a really big deal because it means that more than one type of validator client has been introduced to the Solana network. So there's a lot of like optimizations and things like that that the crew is putting into Fire Dancer, the team from Jump. But ultimately, this is really, really good for just having like different types of validators on the network. And if it's truly going to be much faster and higher throughput than the original like Solana Labs validator, then that's also great too. So you guys are welcome to take a look into that. Jump Crypto is the producer of that. We've also seen the rise of NFTs on Solana. We've seen Magic Eden. We've seen a lot of different collections, you know, come to the forefront on NFTs, and we've seen X NFTs as well, which is a brand new thing. You basically can run full-on applications inside your wallet. So, really cutting edge technology there as far as NFTs go. And that there you can see Backpack right here, which is going to be the wallet that you use to actually run those X NFTs. And then we've also seen the rise of some interesting tooling to build on Solana as well. So this right here is Seahorse Lang. It's a framework for writing Solana programs in Python. And as you can see from the tweet, it actually builds to Anchor. So you've got native Rust, you've got Anchor, and now you've got Seahorse. And currently, as we speak, there's many more frameworks being developed, including some Rust native ones. There's TypeScript, and maybe some more in the future, like Golang. Right, so that's going to be really cool. One day you'll be able to write a Solana program in pretty much whatever your favorite language is to some extent. So that's really awesome. And you can also see here the picture of Toli introducing the Saga phone. Solana Mobile is also coming soon. So we've got a Solana Mobile stack, which will allow you to develop crypto applications native to a mobile phone. And that's powered by the Saga phone and the Solana D app store that lives on the Saga phone. So if you guys don't know about like Solana's new phone or the Saga phone, definitely take a look. You can follow Solana Mobile on Twitter. You can go to the Solana site and take a look at some of the stuff about mobile. But basically, it's going to be a phone that has an embedded hardware wallet, a seed vault, and it's going to allow you to deploy DApp applications to an actual mobile device. So no more like being gated by a DApp store or an app store. So pretty cool stuff. And then you can see here's another little shot of the Saga. And then we also saw Solana Spaces, which is just some really great like support for the Solana brand, the Solana chain, just seeing like IRL connections with this like very digital oriented thing, right? So this was a really cool, unique thing that popped up. And these guys have scaled like crazy ever since. So if you wanted to buy some Solana merch or you wanted to just go have like an IRL experience with maybe some NFTs that you kind of like are a big fan of or whatever, you can check out Solana Spaces. So in general, Solana's mission is to build scalable, user-friendly apps for the world, right? Like the infrastructure that will fundamentally change the digital economy. And if you look at some of the like early on Solana mission statements or like the taglines, you saw blockchain at NASDAQ speed, right? That was kind of like the quote at the beginning. So this is exactly how it aims to do that, right? A really fast blockchain with very inexpensive gas fees and allowing you to be able to build dApps that you don't have to sort of compromise as much on your infrastructure and the structure of your app. So let's kind of dive into why Solana actually enables this kind of thing. And like, I won't go into like excruciating detail on these things, but these are like the top concepts that you might want to understand if you want to know like how Solana kind of works, right? So to get started, proof of history. One of the most difficult problems for blockchain and distributed systems in general is to agree on time. And, Solana kind of solved this problem by introducing what's called a verifiable delay function. And that just means that, like, if I'm going to run this function, I know for certain that it's going to take a specific amount of time within like a very small band of probability, right? So virtually you can assume that it's going to take the same amount of time. And this is really just a hash function, right? So you just create a hash, you run it through, create a new hash, and you do it over and over again, and it takes the exact same amount of time, almost. So you can pretty much assume that that is good for a clock. And that's exactly how this thing kind of works, right? Like you just keep rehashing over and over and over again, and then you can just do the math to tell like how much time has passed. So this was actually a huge deal, even though it sounds like quite simple. This is a big deal, and it works really well to kind of like get consensus on time. Just so you guys are aware, proof of history, contrary to popular belief or maybe some people's belief, is not actually a consensus mechanism. It's just keeping a clock. That's it, right? And that clock is used for many other things, but it has nothing to do with reaching consensus on the blockchain. So just wanted to be straight. Solana is a proof of stake blockchain. But as you can see, a couple bullet points here. So it ensures that the timestamp in any message can be trusted. And as you can see, it's also not a consensus mechanism. So Tower BFT, this is Solana's custom implementation of PBFT, the Byzantine fault tolerance problem. And so this kind of like leverages proof of history as a clock to reduce message overhead and latency. So you don't have to bounce messages back and forth as much anymore because we have an agreeable clock. And that's basically the gist of that. And then Turbine is like how it propagates large amounts of data. And so this has to do with sort of like propagation of account state changes and like a lot of things that we'll kind of cover later in this talk. But ultimately, this is one of the reasons why Solana is so fast is because it can sort of like churn data through the network in a very specific way. And that will become more light, later on in this presentation. Um, so as you can see, here's a demonstration of how Turbine actually works. And you can see that there's a leader elected as Solana's like rotation goes around each block being created. There's a leader. And so you can see that things are kind of categorized into so-called neighborhoods. And all this really has to do with is like when someone requests a transaction or something new has entered, like a request to change a state, that information has to get relayed out to the network. And then a block has to be created and, things have to happen on consensus. And so this is just a method by which this can happen faster by use of groupings and use of like path tracing and stuff like that. So very highly technical, but I would encourage you guys to look into this a little bit more as well. And then Gulfstream is actually quite similar. It ties into it. This allows Solana to process transactions without a mempool. So like on Ethereum, you're probably familiar if you know Ethereum or EVM with the idea of a mempool, which is almost like a queue. And then the validators on Ethereum, or previously miners, would sort of take the transactions that have higher gas first, right? Because they're trying to make more money. And they would sort of put them all into a block and move downwards through the list according to gas fee, pack a block, and then, issue it to the chain and request for that block to be created. With Solana, you basically have all the transactions being forwarded to the soon to be leader. And then that way, once that leader is elected leader and has the authority, so to speak, to create a block, they have all the transactions already like on their node. So they can just grab and go. So there's no like overarching mempool where they have to like pull transactions from and then sort of leave some there. They can like grab these transactions from where they are already and then they can pass the remaining ones along. And so this also optimizes for speed as well. And you can see here's a little graph of pending transactions on Solana. And you can see that, it's pretty steady, except for right in the middle, there was probably some crazy stuff going on. Actually, this is Etherscan, so this might be Ethereum. But either way, you can see this is an idea of pending transactions. So you can see a little bit more information about the Gulfstream, right? And it just talks about how you can, execute transactions ahead of time. You can reduce confirmation times, and you can reduce the memory pressure on validators from the unconfirmed transaction pool. And then finally, we have sea level, which is the runtime of Solana that actually executes your smart contracts. And so the way sea level kind of works is if you've ever used like a thread pool manager in any of your programming languages, it kind of works the same way where it takes a look at like what you're trying to do with a transaction and it applies different locks and figures out what can be done in parallel. So at a very high level, if you think about it, like anytime you want to read data, that can be done in parallel, right? Because you're not changing it. So it's also how a database works. If you're just doing a read, you can do all these reads in parallel. And then the moment a state needs to change, if you're making an edit, then that's when something needs to get locked, right? And it needs to be locked while you're making the change, and then it can be unlocked for reads or writes in the future. That's basically what sea level does. It's just a gigantic thread pool manager for all the data on the Solana chain. So that covers the basics of the technology. Now we're going to kind of get into like some of the programming model around actually building on Solana. So to start with accounts, of course, like the biggest concept that you're going to understand if you're going to build on Solana is that literally everything is an account. And you can see here's like a comparison to a MySQL database where you can see all the different records. And this is like sort of analogous to how Solana works. Like you create data and it gets put into what's called an account. And you can think of this account as like a file. You can think of it as a record. There's a lot of different metaphors you can use. But all it is just a little slice of data on the blockchain. And that slice of data corresponds to its location through what's called an address or a public key. Right. So you can see, like in the example here, each record here might have an ID. And just imagine that ID is just like a giant crypto public key, right? Like it's the same kind of concept. And then the table, which we'll get into later, you can kind of think about as like the schema or like the data structure of that particular account's data. Another comparison that I kind of like to use for this is just like a computer's file system or like a Linux operating system, right? So like if you think about strictly a Linux operating system, everything on Linux is a file. And this actually goes for, pretty much all operating systems, but everything is a file. So even like the most robust software programs consist of a ton of files. And then those files comprise to make all kinds of different things. But your computer is interpreting them as such, files. When you interact with the Solana blockchain, the runtime is interacting with all of the data on the chain, almost like files, right? It's all indexed. So this concept will be really important as you guys learn how to like build on Solana. And then here's an example of what's actually in every single account. So the key things right here are going to be like obviously LAN ports is going to be your balance of SOL in every account. LAN ports being the smaller denomination. And then executable means whether or not this is a smart contract. So if it's executable, then the data in this account is a program or a smart contract. And then the data is just anything you put in that account. And you can see it's a uint data array. That just means it's represented in bytes. So you take some kind of like arbitrary data, you serialize it down to bytes, and you stick it in this account. And that field right there is where that data actually belongs. And then from there, the owner, this one is a little bit trickier to understand. So the owner is actually a smart contract or a program that has the authority to change this account's data. And like this concept is kind of important because you basically have programs that are also accounts, but they have the authority to change other accounts on the chain. And depending on how you write your program, you have to sort of like protect these changes in data with like signer checks, things like that. And we'll cover some of that later. But ultimately, that owner field determines which program can actually like change the data. So, like I said, we'll come back to that, but that's going to be important to understand at like a higher level. So, quick recap: accounts store data and native SOL. Each account has a unique address. An address could be a PDA, which we will probably cover again in some more detail later, but all that means is it's a program derived address, which means the address of the account is derived from the actual program that owns it. So, we'll talk about that later. And then account data storage is paid with rent. This is actually kind of an interesting concept. So, not all blockchains have this. If you want to store data on Solana, you basically have to pay what's called rent. And it's just a small amount of SOL that you pay as a fee to actually reserve that space on the validator hardware. So if you think about it, it kind of makes sense, right? Like validators pay for hardware, like they pay for the storage space associated with it. And so when you want to make a write and store things there, you have to pay for it. It's a very, very almost negligible amount depending on what you want to store, but it is a thing. And you got to actually keep track of it when you go and actually try to create data on the blockchain. So anybody can read from any account freely. That doesn't cost anything, and there's no permission to do that. It's a blockchain. You can read anytime you want freely. And then you can also credit SOL or tokens to anybody's account. And this is what's interesting is because this is how airdrops work, right? Like if I want to send you SOL, you don't have to sign anything. Or if I want to send you an NFT or whatever, you don't have to sign anything. It can just get dropped into your account. So pretty cool stuff there. And then obviously only the owners of the account can do the debiting. They can only like you have to be able to sign for that transaction to take from the account. So now we're going to get into what's called a PDA, right? And so if you take a look at this diagram, um, this might be confusing at first, but if you think about the whole purpose of what these accounts do, is they're designed for you to be able to have data that's sort of like local, so to speak, to your program, and that can kind of be manipulated however your program desires. So, like if you're familiar with Ethereum, your smart contracts have data associated with them, and they're all like local to the smart contract. In Solana, since everything is a global state and it's all represented by accounts, you have to use it, like almost like a custom variation on the account to actually create localized data for a program. Now, there's some variances there, but those will come to light as we explain this process here. But if you take a look, you've got a D app here that can go ahead and create a transaction, send it to the network, and it will create this counter, right? So the program is going to allow for you to create a counter account. And if you look on the right here, this state thing is just an account. That's why the data there has those lines. And the reason you're able to do this is because this, in this case, is an account whose address is derived from this program. And one of the key things about these PDAs is they don't have private keys. So like in typical like crypto or cryptography concepts, like you're probably familiar with the concept of a public key and a private key. And like with any wallet, you have to sign transactions to authorize them. And that's you taking your private key and encrypting the transaction. And then your public key, being public, can then be used to decrypt what you've encrypted. And if that decryption is successful, then that means I can honestly assume that you have the private key. When it comes to these type of accounts that are owned by the program and that are derived from the program's actually able to use an algorithm to make that signature itself. And like this will make more sense when you guys actually start looking at code and you start seeing these up close. You use what's called seeds and you make this address through like deterministic inputs, but ultimately you end up with an account that does not need a private key. So no one person has to like hold the key to make any signatures, right? The program could just do it. So, this is a concept, again, going back to SQL of how PDA might be useful. Like if you have a database that your application from Web 2 is used to just like reading and writing from at will, then it's kind of strange to think that like, okay, if I want to create a new record in a database, I have to like sign for it every time, or like if I want to like update somebody's contact information, or in this case, college enrollment, I would have to like sign for it. Um, Obviously, you don't have to do that if you use these type of accounts, and you can actually create almost like a database, a bunch of different accounts at different addresses using just the program, right? And you just have to derive these addresses through some kind of function. So you can see here is just like a little bit of a demo of how this might look. So we're just comparing these IDs to public keys. I just got these represented here by like this like truncated public key sort of syntax. And you can think about it that way. And then you can see that like here's the function that you use inside the SDKs on Solana to actually find these keys. So if I use the ID from, let's say, the database table that we're here, right? Let's say I'm like transposing all this data onto the blockchain. I could just use that ID field as what's called a seed. And then I just provide that input with my program and I get a public key. And then I provide the next ID, right? And just so on and so forth. And you get an address. And the cool thing is, you don't need to store that address anywhere. So as long as I have the ID, I can get this person's on-chain address. And then you can think about it more in like a design implementation for a D app. You can kind of like use seeds that you know are going to be deterministic, and then you can find somebody's information. Like, for example, if I'm interacting with your app and I have my wallet like connected to your website, then you have my public key, and you can just put like a string there as like a constant. And let's say it's like, I don't know, like points scored, right? Something like the challenger maybe or whatever. You could say like the string points scored hashed with my public key, my address is going to give you the account that has that data. And that's like how a lot of these apps kind of work. So that's how you can actually get data that's like sort of native, so to speak, to your program. So before we get into rent, if anybody has any questions, I would love to take any. I know the PDA concept can be a little bit confusing. So like if anybody has any questions about accounts or PDAs, go ahead, let me know. I'll just take a minute to see if you guys have any. All right, cool. I'm gonna go with everybody's good for now. So on to the topic of rent. We touched on this, right? Like story data is not free. Validators have to pay for this. So, the way rent kind of works right now is a little bit confusing because at first it was like you just pay for how much space and you have to make sure you're kind of like depositing enough. And then the concept was introduced to be rent exempt, where you can basically put in like 2 years of rent. And once you have enough rent in there for that amount of time, you don't actually have to pay rent. So it like sounds a little crazy, but ultimately now the standard, like the de facto, is to just put in enough rent to be rent exempt. And then as long as your account holds that much SOL or Lamports, because it's really not, it's only a fraction of SOL, then you're not able to pay rent or you're not required to pay rent. You can just sort of store the data there and then you're good to go. Nothing will change about your balance. And then here's an example of actually calculating the rent from like this looks like TypeScript. So you can just use a Solana connection. You can get the minimum balance for rent exemption, and you can pass in the size of the data you want to store. So pretty straightforward. And then you can see some information about rent here if you use the command line. And now let's get on to the cool part, right? Let's get on to like smart contracts and programs. So diving into programs, special kind of account where that data field is actually bytecode that represents an executable program. You can write these in Rust, C, Python, and Solidity. The Solidity stuff is still in development right now, but soon you'll be able to actually write Solidity contracts and deploy them to Solana, which will be pretty cool. And then programs are stateless. So they read and write data to other accounts, but they don't hold any state of their own. The only thing they hold is a balance of SOL. But that's pretty much arbitrary to all the different data that you're going to be manipulating. And then programs must be the owner of an account to change its data, which we talked about a little bit earlier as well. And then they process what's called instructions. And so when you create a transaction for the Solana network, it has a list of instructions in it, and each one of these instructions is for a specific program. So your program has to be able to process some kind of instruction, and they actually do follow a format that we'll see too. And then programs can actually send instructions to other programs too, which is called CPI or cross program invocation. And that's how you can basically use another program that's authorized to change data of accounts when you're not, right? So think of an example of like transferring a token. In that case, the token program is the one authorized to do that, and your program isn't. So you'd have to call the token program and request a transfer, and then it would return to you whether or not that succeeded. So pretty cool stuff. So let's talk about transactions, right? So this right here says they're atomic. And what that basically means is everything you put into a transaction has to succeed in order for a transaction to succeed. And it actually won't allow these state changes if the transaction fails. And you can actually see this real time when you're developing through what's called a transaction simulation. And basically, it'll take a look at all the different instructions and all the signatures and all the metadata associated and et cetera, and make sure everything checks out before sending it to the network. And if anything fails, it'll unwrap itself. So imagine like you want to sell somebody an NFT and they say they're going to pay you like 100 SOL and then they don't have it. If the instructions were transfer NFT and then transfer SOL, you would think like naturally, okay, my NFT is gonna be gone if that transfer of SOL fails. But like that's actually not how it works. If the transfer of SOL fails, the previous instruction to transfer the NFT would also fail. It would be unrolled. So that's all that atomic means. And this is what an actual like instruction looks like. So like I said, transactions have a list of these. And you can see there the program ID is what smart contract we're pointing to, right? And then you've got the data, which is what tells the program what to do. And then the keys, which are just going to be all the accounts that we need to involve in this process. Whether or not we're reading or writing, you can see that Boolean right there. That's going to be what we tell the program. And then this ties back to like the whole C level thing where you basically using these configs, you can figure out whether or not something can be done in parallel. So like if all those things were is writable false, then you could run this program like 100 times at once and you would never have any kind of like locks involved because it would be all reads, right? So pretty cool. And then here's just an example again, list of instructions, some signatures, and a recent block hash. And the recent block hash is a security measure. So like when you send a transaction, you're supposed to grab a recent block hash to put into it. And that's because like the network will actually take a look to make sure that that block hash isn't too old. Just to kind of like maximize security there, make sure that like it's not like stale or whatever. So max size for transactions, and then there's also compute limits for transactions. So there's a couple of like constraints associated with these kinds of things, which are not super important to go into super detail right here, but just be advised that these do exist. And like I said about the recent block hash, and then any account marked as a signer must sign the whole transaction, right? And this is actually important because the transaction has to be like created and in a what's what I want to consider a finished state, right? Like you're not adding anything else to it. And the last thing you can do is sign it. And like we talked about earlier, that will encrypt the whole thing with the private key. And then that encrypted bit of that transaction, all of those bytes, will actually get passed into the runtime. And then, like I said, you'll use the public key of the signer to make sure that it was, in fact, signed by that private key. So that's all this means, but it encrypts the whole transaction. And you can see one account must sign to pay the network's transaction fee. That's going to be what you might know as gas. And one thing that's cool is like you can pay gas on a transaction if you're not involved in a transaction. You still have to sign it because like you're debiting yourself to pay for it, but like I could pay for a transaction that creates you a bunch of stuff. So something worth mentioning. And then here's the different like instructions of programs broken down again, right? So the program ID, the list of accounts, the instruction data, you can see that here's just like a different way to view what we just talked about. So program ID is going to be your program. If this instruction reaches your program, that means like that was pointed at you. These are the accounts that are going to be involved with whatever it is your program's about to do. And then the instructions are what it's going to do. And this might not make sense at first, but think about the instruction data as like it comes in as bytes. And then if you write your program in Rust, it's going to convert those bytes into Rust code. And then that Rust code is going to have the different configurations that tell your function what to do. So like think about like getting a variable into a function. If it was like an enum, right? Because that's what some of these instructions actually look like. Depending on what that variant of that enum is what your function is going to actually do. So like think about like if statements, match statements, whatever. That's all this instruction data really means. So just diving a little bit more into instructions. A program can only interact with the accounts that are passed in on that accounts list. So if it's not in there, you can't actually access them because the runtime is granting your program access on entry point from that list. And then you can implement authorization requiring an account to sign. We kind of beat on that a little bit. And then here's an example of transferring tokens. And in this case, we haven't actually talked about this, but Solana has a collection of programs that are what we call native to the chain or to the network. And these programs are designed to do like very like integral functions for the blockchain itself. So you can see here we're referencing the system program, and this one is the one that creates new accounts, that can allocate space, and that can change the ownership of accounts. And then there's other programs like the token program, which manages all of your SPL token functionality, like transfers and creating mints and stuff like that. And then there's even other ones too, like associated token accounts. There's the new lookup table program. There's a lot of different programs that are already native on the chain. And what's interesting about that is you can actually leverage these to do a lot of your functionality without even writing your own program. So like you can build a Solana app that just integrates the system program, the token program, a couple other programs, even like the metadata program for NFTs, and you never have to write any Rust. So we'll touch on that a little bit more, but the point is these programs live there already for that reason. So in this example, we're just going to transfer some tokens from sender to the receiver. You can see the sender is the signer. Both of those are writable because we're going to be changing their data. And then we need to also include that system program because we need to actually load and possibly lock that account that's going to be actually doing those transfers. So again, we see this diagram here. All this really is saying is like when you invoke another program, it looks exactly the same. You still have the instructions that are being passed over to these programs. So looks exactly the same as if it was hitting your program. And now let's talk a little bit about like the clusters and some of the infrastructure. So like for those of you guys who don't know, there's three clusters that are really your main ones that are public. And then there's also a local cluster you can set up if you download the toolkit, which will just give you a single node validator on your own computer that you can just run and deploy programs to and test stuff on. So it's usually a lot faster and it also costs you nothing. DevNet and testnet don't cost you anything either. DevNet's the only one you can airdrop on. And then mainnet's going to be the one that actually costs you real money. So you can see here some information about each cluster. So, you know, some things about DevNet, that's usually the most common one that people will deploy programs to. Testnet, you can do the same thing, but testnet is often used to test new features to mainnet, whereas DevNet is sort of like a sandbox for you guys to just go ahead and deploy programs to and mess around. And like I said, DevNet allows a faucet where you can sort of receive airdropped SOL, but it's pretty rate limited and you do want to actually be careful because like you can't just go crazy. So a lot of times just doing a single node validator on your local setup is the fastest way to get something built until you're ready to go to DevNet. So here we're going to take a look at a counter program. And this is going to take a look at the actual flow of building a program. So if we want to have the instructions for incrementing and decrementing a counter, you can see that here's the account that we're going to actually use to store this data. So we just got one field, it's a U64, and we're going to store a number in there. And anytime we hit the increment function or instruction, we're going to increase and obviously decrement, decrease. So this is how it actually looks like when you interact with the blockchain. And we saw this diagram earlier, but now we're going to apply this diagram to our live like counter example. So we're going to go from our D app on the client side, we're going to hit an RPC node, and that RPC node is going to propagate our transaction to the network, where it's then going to be processed by the validators, in this case, the current leader. And then that transaction is going to split out our instructions, one of which is going to be for our program. And it's going to actually go to our program itself and execute whatever instruction we pass to it. And let's say it's incrementing one or decrementing, doesn't matter. We are going to just update the state of that account. In this case, it goes up to one, right? So that's the flow. And hopefully this makes more sense than the first time we looked at this diagram, but you can see that we have to go through this RPC node. And now from RPC backward, this is pretty much like almost the same thing, at least like from a field perspective, as like doing HTTP requests. The only difference is like you have to actually build a transaction and do that kind of stuff only when you want to change state. When you want to just read, you just do an RPC get, and it literally feels the same thing as just doing a get request. So pretty cool. And then from the RPC onward, that's where you actually enter the Solana network, the Solana runtime. And then these sort of things start to take place inside of that that might behave a little bit differently than what you might be used to. And you can see here's a little bit of information about that as well. Now, we're going to talk about the life cycle of a transaction here. Now, transactions are ingested by the current leader, the validator that's currently elected as a leader. They then filter the valid transactions, and then they execute the valid transactions, updating state on the chain. It packages those into entries, and then it transmits those entries to the validator nodes in signed shreds. And then those validators retransmit the entries to their peers, and they further downstream pass this information to all the other nodes. And then they can actually go ahead and validate those transactions and execute them on all of their state. And then at specific times, validators transmit votes to the leader, and then they observe their votes and all the votes from the cluster. Oh, whoops, went a little too fast. And that's how they eventually reach consensus on a new block. So, that's exactly the detailed flow of a transaction. That's really it, guys. Those are the basics for building on Solana. I hope that was helpful to you guys, and I would love to take any questions you might have about some of the concepts, like maybe anything that wasn't clear. We kind of covered a lot, so by all means, anything you guys might have. Yeah, no doubt. So I'm gonna just pull up a browser real quick. I'll do a quick once over of some really great resources. So your best friend building on Solana is going to be the Solana Cookbook. And this is a really good site with a lot of like reference implementations. It talks a little bit more about the concepts. And you can see like here's some examples of how to do some common like Solana development things. And then if you look at our Solana developers repo on GitHub, this will actually have a lot of useful stuff too. So there's the cookbook. You can see the workshops, some reference examples for on-chain programs, off-chain code, and also this cool CLI, which I'm going to show you guys how this kind of works in a sec. Let me see. You can basically create for yourself a full-on Solana app by just going like this. You can type npx create Solana D app, and that should be npx space. And then you just name it like my app, and it'll just go ahead and create for you a brand new Solana repo for like a program, a front end, like all the stuff that you'll need, all the configs. So if you want to start building, this is actually a great way to do it. And once it gets done, it'll just have everything installed for you, which is pretty cool. Other than that, though, there's some really great resources. If you follow a couple different folks on Twitter and people from Solana, like there's some really great people that are just involved in the ecosystem, really vocal on Twitter. And then you can also catch us on YouTube at the Solana YouTube, which I don't exactly have a link to, but if you go to YouTube, you can just search Solana and you can just filter by channel and you can find us right here. And there's a lot of really great useful info on here as well, including the core community call, which is just getting started, just brand new. A lot of cool updates there. Some getting started on Solana videos specifically for Grizzlython. And then there's also stuff like, if you take a look here, there's going to be the change log, which is some updates to Solana, and the Solana Bytes, which is just going to be some overall tutorials about the basics that we just covered. And that should be everything you guys need, honestly.